Okay, let's get started. So we're really happy to have Tadashi Takayanagi here to tell us about pseudo entropy and stuff.
Okay, first, I'd like to thank organizers for giving me a chance to give a talk here under this really stimulating workshop. And here, I'd like to talk about some generalization of entanglement entropy, which we call pseudo entropy and its connection to holography. But my talk is consists of many two parts. And the first part, I'd like to give, thinking this broad audience, I would like to give some introduction to the connection between entanglement and holography, also highly motivated by recent, very interesting work by Boland, Pfefferman, and Barizani, and about this connection, interpretation of area safety from the viewpoint of computational complexity. And I want to give some discussion, discussion from based on our earlier work, and then go to main part of this talk about pseudo entropy. And this is actually quantity which generalize entanglement entropy or holographic entanglement in the setup with post-selection, as we will explain. And I should apologize. This is a bit different from the pseudo entanglement, which will be, I think, many talks tomorrow. But both are, of course, related to holography, and I think both will help us to understand holography very much. Okay, so this pseudo entropy part is based on these works, and mainly this first work by these people and collaborators Yoshifumi Nakata and Yusuke Taki and Kotaro Tamaoka, and Jisha Wei. Jisha is sitting there, and he's a main player, so he can ask. I think he can answer some main hard questions. And so these are some relevant also further progresses, which I will mention briefly in this talk. Okay, so let me start with this entanglement and holography. And historically, this is based on the following interesting connection. This is a historical motivation why we think, why we relate gravity and entanglement and holography. And so this is a black hole space-time, also as in Geoff's talk just morning, and also Lenny's colloquium is on Monday. So we have some gravitational space-time, and we have some black hole, and observer is outside, and observer try to see inside the black hole, but because of strong gravitational force, observer cannot see even light rays coming from the black holes. So in the black hole, we expect some degree of freedom is hidden, and the hidden amount of information, this is measured by black hole entropy, and which has a very beautiful formula, Bekenstein-Hawking formula, like this. About this black hole entropy and given by area of black hole instead of volume, and area divided by 4G Newton constant. And observer so try to see this, but the observer see this kind of ambiguity of information given by this black hole entropy. But maybe more quantum mechanical viewpoint, we might think this black hole and outside part is highly entangled. And so this and also here, of course, it's a black hole entropy follows this area law, but area law also appears in different fields, like namely, if we think of quantum many-body systems, and this is a kind of spin, quantum spins, and we separate Hilbert space in A and B, and observer is sitting A, and B is only these 9 spins, and let's assume this observer cannot access to the spins inside, then observer have some ambiguity of information, and if there are quantum entanglement, this entanglement entropy gives kind of this lost information or hidden information inside B. And that also, again, follows area law. And this is originally, historically, this is the original reason why people think about the entanglement entropy quantum many-body system and aiming at to understand black hole entropy. So they have both have some nice area law, but there are significant difference. This guy has model dependent. It depends on what kind of spin field, what kind of matter, what kind of how many different kind of spins, and it really depends on that. Also, it's a UV divergent. That means we have this. If we have infinitely many spins, this quantity gets divergent. But in black hole entropy, we have a very beautiful universal formula. So it looks different, but in the end, holography can help us to understand this connection very simply. And also, we can also understand this area law of this quantum many-body system, also related to some quantum correction to black hole entropy. And so let me first explain some of these, just each side in very elementary way. So entanglement, of course, already appears in many talks in this workshop. And what I had in mind is just decompose Hilbert space into two parts, A and B. So this region on outside, and total we have some single quantum wave function, single quantum states, and we trace out because observer see only A and outside C is not B is not accessible, so we trace out some B, and then observers in A see this reduced density matrix, this probability distribution, and then the amount of this entanglement or amount of the lost information, because originally we have a definite information, but after tracing out B, we lose some information, and this is measured by entanglement. This is a Shannon, quantum version of Shannon entropy, just low. This is what I had in mind for entanglement entropy. And so in particle physics or high energy physics, also string theory, we often consider some continuum limit, because the original ADS-CFT correspondence also formulated in a continuum quantum field theory. So that means, roughly speaking, we can take this that is constant. This is, distance between two spins goes to 0, and then we have a really continuum spacetime, and this discretized boundary, it now becomes smooth boundary here. So that, anyway, once we specify A and B, separation between A and B, then we can define entanglement. This is basically setup we are thinking. And also in quantum information, there is a very interesting, very useful operational viewpoint, which just quickly summarizing in this slide. And so we have some quantum wave function psi, but let's take some very many copies. But anyway, so each wave function is a very complicated. Entanglement is very complicated. This is A and B, but this spin is entangled with this guy, also this guy, and many complicated ways. But by acting realistic operation called LOCC, this means that local operation, which means a quantum operation on A and B independently. And we can do some also classical communication, A and B. Let's assume A and B are separated laboratory, and they are far apart. Then we can do some quantum operation each laboratory. But from distant laboratory, we can only send information classically, like emails or making phone and so on. And then we can rearrange this entanglement into very beautiful just some number of Bell pairs, EPR pairs. And then, so we can think about this process that we can take many copy of this original system, and we can distill some number of Bell pairs, also with some contamination. But we can maximize this number of Bell pairs, and let's call it n. Then we can take ratio. So this ratio is n divided by m. This means for each state, for each one copy of quantum state, how many Bell pairs we can extract. And this has a very nice limit. And this very well-known theorem in quantum information tells us this coincides with this algebraically defined von Neumann entanglement entropy. So these are quite useful way to understand entanglement entropy on this side. So now I'm going to this gravity side. Already explained, but let me give some once more. So gravitational, so this originally of course start from this black hole entropy formula. So entropy of black hole is given by area of black hole divided by Newton constant. And this is not volume, but volume. This suggests that degree of freedom in gravity is proportional to area rather than volume. Usually in usual matter and gas and so on. So usual things, entropy is proportional to volume in thermodynamics. But here it's unusual. And this motivates us to understand, us to find this holography found by Topf-Saskin. And this is a schematical picture. So we have a gravitational spacetime on some manifold and some spacetime, but actually real degree of freedom in terms of some quantum matter without any gravity is larger, one dimension lower, squeezed to on some screen. So we can project degree of freedom onto a screen. So then actually degree of freedom counting roughly, of course, matches because black hole entropy is here, it's a proportion to area, but this because one dimension lower. So degree of freedom of matter is now entropy of matter looks like proportion to volume here. So this is a heuristic picture of holographic duality. But this, of course, this is quite abstract. And can we find good example? And this is a ADS-CFT correspondence. This is quite most very established holographic principle. And this tells us, this is a bit, of course, technical, there are many terminology here. But basically, this tells us, as in Geoff's talk this in the morning, So we have some anti-Dogita space-time called anti-Dogita space. Anti-Dogita space has a special feature that there is a boundary. So this boundary plays a very important role, and indeed this degree of freedom in the bulk is somehow reflected at the boundary. So this bulk gravity, bulk gravity, which namely gravity on anti-Dogita space, is actually becomes equivalent to some boundary degree of freedom, and the boundary from some symmetric constellation and many string theory input suggests that this is a theory with some gapless quantum system. And the more precise, more formal terminal is a conformal field theory, CFT. We call it CFT, but it's sort of quantum manual system at critical point, like gapless quantum system. And our favorite limit, more precise, we take a favorite limit that is a classical gravity limit. Then you can just use Einstein's relativity. It's much easier to calculate. Forget about string theory, forget about quantum gravity limit. Then this limit corresponds to, in this side, this quantum system language, it's like strongly interacting. It's very difficult to analyze, actually, but it's strongly interacting quantum manual system is actually equivalent to general relativity. This is a basic statement of this ADS-CFT correspondence. So these are holography and ADS-CFT correspondence. Now I got relation to quantum entanglement, quantum information. So this is a calculation of entanglement entropy in ADS-CFT correspondence. So this here is this is an anti-Dogita space, some space-time with a boundary. So we have a boundary here. And at the boundary, we have some quantum system, quantum critical system. And we decompose Hilbert space into A and B by just specifying particular border of the region A. And here we omit time direction because we are talking about completely static, no time dependence. It's just like ground state or energy eigenstate. There are no time evolution. Let's think about such a state. Then it looks like static space-time, and it's given by some anti-Dogita space or some deformation of that, static deformation of that. And then boundary, we have some quantum system, or in this language, we call it the conformal field theory. It's one dimension. Here it's bulk is d+2, then d+1. And then we decompose Hilbert space into A and B, and we are talking about entanglement between this A and B. And how we can compute it? Of course, we can compute in quantum system. It's very complicated, but we can compute it. But in the gravity side, one dimension higher, so we can extend this boundary towards the bulk, like this way. And of course, there are infinitely many extensions, but we pick a particular one which minimize area, minimizing. So that uniquely picks up the nice surface. And in ADS, it's non-trivial surface. And just calculate this area and divide it by, we divide it by 4G Newton. This is originally, of course, same as Bekenstein-Hawking formula, black hole, but this is no longer any, there are no black hole here, just no horizon. This is not horizon. But anyway, we can apply same formula, but the new thing is a minimization. Then this actually coincides with entanglement entropy between in this quantum system A and B. And one more point is that here we have this direction, z direction. In holography, we have one extra dimension. And if this direction goes to the boundary limit, z equals 0, at the boundary z equals to 0, and then metric divergence, the size of space-time divergent. This divergence, it's a very huge space appears here. And that divergence is related to this UV divergent, ultraviolet divergent, which we encounter in this area of entanglement entropy. So leading divergence corresponds. So we need some geometrical cutoff. So we slightly shift the boundary by small, very infinitesimally small amount. So we need an epsilon here. Okay, so by using this framework, we can evaluate entanglement. And in general, for generic shape of A subsystem, we can get some series expansion in terms of epsilon, this UV cutoff. So leading divergence is precisely reproduce area law divergence, which is we know very much in quantum system. And we can get also sub-leading divergence. And but this also depends on the dimension. Total dimension is odd, including time direction. Odd dimensional conformal field theory has an envelope is constant, which is for special shape. It's round shape. It's called F quantity, which plays a very important thing in quantum field theory. And if total dimension is even, then we end up with some logarithmic divergence. And this logarithmic divergence is also important in high energy physics. This is like called conformal anomaly. Some anomaly appears, and that's we can. This is a good way to calculate this.
Evolutions are this done in the ground state or any excited?
Good question. Yeah, actually, we can do the both cases, and this result is true for even excited states. Yes, I mean moderately excited states, finite energy excited state. This is true. But for ground state, we can do this calculation analytically for nice shape. Then we can precisely fix this constant. But in general, we can numerically calculate this constant. Okay. And so by using this geometrical picture, we can derive some non-trivial inequality which is satisfied by entanglement entropy. So this is one. So basic one most basic inequality is called strong subadditivity which is satisfied for von Neumann entropy. It's just simply due to this kind of triangle inequality looks like. SAB means A union B. So this SAB is this related to this minimal surface area, red guy. And SBC is related to this blue guy. But we can recombine this way, this green guy and this kind of brown guy. And but this is obviously not smooth. So there is a nice smooth surface which minimizes really area, which covers ABC and B also. So that is this inequality is a little bit trivial. It's like a triangle inequality. And we can do the similar thing for another recombination, get another inequality. So also these two guys are called strong subadditivity. And so that way, so algebraic properties in quantum information, which often very technically complicated, but becomes quite a simple geometry in gravity side. So this is how also this concept of ADS-CFT usually. So algebraic thing becomes geometry in gravity. So now I'm slightly go further that we would like to also understand some more general version. So first one, this one is like covariant version, namely it's time dependence. So we are talking about real time dependence. We have some system and we think of generic excited states, then we have a non-trivial time dependence. So here we have a ground state is just pure ADS, it's no time evolution, but we kick out something, then if we have some non-trivial evolution and it's gravitational waves and so on. So that case, but still this works. So we can, so this is quantum state time dependent, and we can define reduced density matrix, which becomes time dependent entropy. But this entropy, time dependent entropy, can be geometrically computed by this formula. So this is basically what we do, almost same, but little bit different point is that extremalization. This is everything is Lorentzian, time direction and space direction. And if we go to null direction, right-like direction, area becomes zero because there are no length, it becomes zero in right-like direction. So minimum area don't work. So instead, we just require some saddle point condition, like extremalization. If we extremalize area, then it's just zero. So this is extremal surface. So this is called extremal surface. And if there are discrete number of candidates, we can just minimize it, and then that gives correct answer to this calculation.
So one quick question about the previous slide. So now people know even stronger versions of strong subadditivity, like the condition which information is more than some number technical stuff. Is there any operational interpretation of that in this framework?
Operational interpretation.
Like some interpretation in terms of gravity.
Yeah, so anyway, yeah, there is also stronger version of this inequality. I think Patrick and collaborator found like this called monogamy of mutual information. And that actually also tells us, I mean, not all quantum states satisfy, but only gravity theory have satisfied particular inequality. And that kind of inequality also more generalized entropy cone. It's not known. And that I think help us to understand what is the quantum nature of quantum state due to gravity. But real, I mean, if we talk about LOCC like operation, it's very so far in my understanding it's not easy to do it in gravity. I think it's quite interesting question. But so far, as far as I know, it's not that useful to think. Okay, that's a good question. So now, okay, so these are time-dependent case, and now I'd like to talk about some kind of how ADS-CFT looks like based on this idea, based on this consideration about quantum entanglement. So this is an emergent space from quantum entanglement. Also, I would like to also mention complexity, and this is I think main topic of this workshop. And we can combine these two actually in this formulation. I will explain. So this anyway, this holographic calculation of entanglement suggests that we get some 1 qubit of entanglement for each Planck length area. So this area divided by 4 times Newton constant, but Newton constant is just power of Planck length. Planck length is given by this. It consists of fundamental constant in physics, and it's just very small. I mean, to 10 to the 35 meter. It's like we believe this is a minimum size of length scale in quantum gravity, and below that we have an extremely heavy quantum effect appears, and I mean we cannot trust this classical geometry. So, but this is some characteristic length, very small length appears, and this is the area divided by that. That means for each Planck unit length area, we get a 1 qubit, 1 entanglement, 1 EPR pairs, 1 Bell pairs. But we can change the size of A, and you can change the location of A as you like, and then it looks like this space-time is filled with these EPR pairs to understand this formula. And that, of course, that's a very abstract way of saying, but actually there is a nice framework which we can realize this idea is so-called tensor network, which also I think it's useful for quantum computation. I had many interesting talks. And tensor network is already, I think, discussed many people, so I don't need to probably introduce this. But this is a nice graphical description of quantum state and which respects quantum entanglement. And so in the context of ADS safety correspondence, there is a nice tensor network which is called MERA, multi-scale entanglement renormalization on that. Found by and this is a nice tensor network which describes conformal field theory, ground state. So gapless conformal field theory. And then if we think this kind of network, anti-Dojita space-like structure naturally emerges. So there is many spins. We want to compute this quantum state for these spins, but we construct the wave function by contracting tensors by unitaries and isometries and so on. So this structure is scale invariant, and somehow nice geometrical structure of qubit appears. This is a claim first noticed by Brian Singer. So it's like looks like maybe tensor network gives some way to understand emergent space of an anti-Dojita space in terms of some quantum entanglement. And there are, of course, refined versions, very nice models like happy models, which based on quantum error correcting codes, and also random tensor network models by Patrick and collaborators, which is a nice property that it precisely gives this entanglement entropy as a minimum length. So, but here I'd like to talk about one more idea to understand this discretized space-time, which is like something called path integral optimization by these with my collaborators. So here, what I had imagined, of course, in the end, we want to relate this to ADS safety. We want some continuum theory, quantum field theory. It's epsilon of 0. But also, more importantly, so we are talking about anti-Dojita space, and this is a time direction, but we are interested in some space, time slice volume, time slice. So it looks like, this guy looks like also time slice of anti-Dojita space, namely hyperbolic space. But hyperbolic space is Euclidean space. So it might be also natural to think that is a kind of quite Euclidean, or in terms of quantum gates, it might be non-unitary gates active. So then actually in the high energy theory, this kind of idea is often used because we usually create quantum state by Feynman path integral. In path integral, but we are talking Euclidean path integral using imaginary time. And so basically idea is to take any quantum state, any boundary condition, but we act this exponential minus th. T is a time, Euclidean time, imaginary time. And t goes to infinity, of course, it's projected down to ground state. And this is a quite useful, powerful method which we often use. So actually, ADS safety also maybe can be understood in terms of that kind of operation. So here, idea is to we discretize this path integral and minimize computational cost. If we imagine we can just do this calculation in computer, we have there are many tensors here and contract each other. We want to minimize computational costs. Then, so idea is just initial state, we can coarse grain quite a lot. So initial state, initial time evolution not so important. So we can coarse grain, but finally fine grain to recover correct ground state of some quantum critical point. So then this actually, in terms of tensor language, it looks like also similar to this tensor, but it's each vertices and tensor is a non-unitary. So, but anyway, the good thing is we can indeed explicitly evaluate this computation because this is a complexity, computational complexity, but in terms of non-unitary gates, and mathematically we can minimize it. Mathematically, this is actually related to something called Liouville quantum field theory, but this is a technique I'm not going to details. But by minimizing such a functional, we can completely precisely recover anti-Dogita space, like also similar way, like here. So we get a time slice of anti-Dogita space, which is really space-like. So here there are some kind of discussion between, in the light of this recent interesting connection between computation complexity and area safety. So, but here, so this minimization of this computation cost are somehow related to leads to some gravity because you can put some object here, but once you put the object, we can extract a lot of information of this object. So you need some fine graining nearby this object. This in this actual calculation we put some operator. Then we have to fine grain. This is fine grain. So then one side corresponds to 1 unit area. 1 unit area. So this basically, once you have discretization, you can have a metric, but you have a lot of this fine graining, so that changes the metric, and it's much like a general relativity. If you have some putting some object, then it expands space-time, and it back reacts. So this kind of idea also looks similar. I mean, it's at least qualitatively, so sometimes it's quantitatively. I mean, matches with general relativity, some idea. And thinking that way, so just some small comments, some discussion. But so here in this picture, area safety, to understand the emergent space area safety, might be related to some more non-unitary gates rather than this unitary gates. And then, so this thanks to my colleagues in our institute, Tomoyuki Morimae and Ryu Hayakawa, and they're also expert of complexity, computational complexity. If so, then this complexity class is much like not just BQP, but it's a post-BQP. It's a lot of post selection, and which is much powerful as far as I understand. It might also, this I think might be also another interesting possibility. So I'm not completely expert of this computation complexity, so I cannot say more than that, but just one suggestion. Yeah. Yes.
Can you say a bit more about why we need non-unitary gates?
Yeah. Okay. Yeah. So, okay, if you have some anti-Dogita space, right? And we want to create a quantum state. We want to, usually we have some time slice. Time slice corresponds to quantum state. Then it's natural to associate with time slice of bulk, in the bulk. Right? This is a completely space-like. And if we think there are no causality, no right coordinate of such a structure, and it looks like space-like. But if we look at this like real tensors, like the mirror tensors, these guys are unitary and so on. Isometry, and there are some causal structure. There is also such a, argument. I think first pointed out by Bartek-Czech, some mismatch between this causal structure. So now I go to switch. I go to Pseudo Entropy. So if you have a question, maybe. Yes.
So when you do the post-selection, I'm wondering so the power really corresponds to the probability of the event you are post-selecting on, right? So what's the probability of the event you are post-selecting on? That's super small.
Yes, I think I just doing some kind of these operations to eliminate some other unwanted sectors. So not exactly doing this post-selection, to be honest. So I don't know the precise details, but it's most naturally related. Thank you. Well, probably we can formulate precisely. Yes.
So in the imaginary time cases, does it become something to do with random, continuous time random?
So random walk.
Is it something that thing looks kind of like a continuous time random? Is there some relation to it?
Yeah, but this is Hamiltonian, not exactly completely random in my understanding. In usual physics, it's close to some. Quite random system, but not exactly the same. It's also scrambling. It's a scrambled state, but not as fast as a real random time evolution. Yeah, I think that difference is quite important. Okay. So now, okay, so let me go to this mainstream of this talk, but I think it's a kind of just naturally connected. I just want to discuss, present some third formula of this holographic entropy. So first formula is static space-time, right? Minimal surface gives an entanglement entropy. And second formula is time-dependent case. Time-dependent case, we can use this, not minimal surface, but we can use extremal surface. We extremalize area. But there is actually third one, that is actually Euclidean time-dependent case. So usually we think usually real-time dependent. And so why we consider some Euclidean imaginary time evolution. But this is, of course, it's important in a tunneling process in physics, but also theoretically it's quite useful. So Euclidean time dependence is useful because area safety is often discussed in the setup completely Euclidean setup without a real time and imaginary time. Instead of in real time, we consider imaginary time. Then we can have many nice mathematical structure and so on. So in that case, the question is what kind of quantum information quantity in CFT correspondence correspond to that one? And the answer is something which we call pseudo entropy. And so just let me define pseudo entropy. And this is a kind of just generalization of entanglement entropy to two quantum states. So this is a kind of post-selection. So we have an initial state psi, and finally post-selected by bar phi state. And this is a matrix which are interested in. This is what we call transition matrix. This is no longer Hermitian. So it's not the usual quantum states. We generalize the idea of state here. But let's see. So we also, again, we can just trace out some part region. So we have a factorization of Hilbert space, and we just trace out B. This is a reduced transition matrix. And just mimics what we did for entanglement entropy. So we can define tau A and tau A log tau A, the low, like von Neumann entropy. We just we replace low with tau. And we can talk about this Rényi version to the nth power, Rényi version. And so there's some nice property like this. It's like, the first one is a very, not nice. This first one is a very important part. It's in general, this tau A is not Hermitian. So that means this quantity is not guaranteed to be non-negative, as usual in entropy, non-negative real part. It's actually in general complex minor. So especially imaginary part, we have to be worried about what does it mean, and it is quite important. But the real part has a better interpretation more in terms of entanglement, as you see. So, and if there are no entanglement, either psi or bar phi has no entanglement, this quantity is 0. And we have some, if we replace the initial state, final state, then it becomes complex conjugate. And we have SA equals B like equality, because essentially just a pure state. And if, of course, if these two states, initial state and final state, the same, then this quantity is just the usual entanglement as Rényi entropy or entanglement. And so, this kind of post-selection also discussed in many kind of contexts. And so if you think particular operator, Hermitian operator, but if we post-select it, then it's no longer to be real value. This is called weak value. And this is a kind of weak value of entropy. So should entropy some, and more precisely, weak value of this something modular operator. Right? But this turns out to be area operator. This is really, in holography, this becomes area. So yeah, the good thing of this quantity, why we consider such a quantity is because we have some nice holographic formula. So you have some Euclidean imaginary time-dependent ADS spacetime, but still this is the ADS, so it's like we can define nice minimal surface, and what's the quantum information theoretical meaning of this guy? And it turns out this pseudo entropy is precisely agreed. So the derivation maybe at first sight maybe looks surprising, but this is not surprising. Actually, if we remember, just if we think this, derivation of holographic entanglement is from the ADS safety correspondence, we can actually naturally got this relation using deprecatory. And we can confirm this basic properties like this. If everything pure, then this becomes trivial because they cover everything, and they say for this and some it's a kind of almost obvious.
Could you just clarify what psi and phi you plug into the formula for this to work? Is one of them like the initial state?
Yes. Exactly. Yeah, exactly. Thank you very much. Yeah, sorry, I missed that. Yeah. Okay, that's simple. So here, this is a Euclidean path integral. So this first part of path integral creates some one particular state psi, but we have other path integral plus infinity to some time, and that creates another state about phi. And yeah, if we just do some gravitational path integral, we just take an inner product between two different states. But here we insert some non-trivial thing and pick up some descent. Okay, yeah. Then, so what we actually, so one interpretation of this quantity, so we can understand it as some entanglement distribution, which I mentioned before. That is true that is well known in entanglement case. But here we only have a particular case. We can only relate. We can only entanglement distribution for particular case, which is where we can diagonalize psi and bar phi at the same time, like this way. Then we have this pseudo entropy, and we can reproduce pseudo entropy from Bell pairs, number of average Bell pairs, which we can extract from intermediate states. So of course, this is not completely satisfactory. So that means maybe we can define another quantity, which is what we did recently. So this quantity, unfortunately, don't have a gravity dual. So it's more, I mean, it's a good in that sense. This quantity is always non-negative and bounded by dimension. This is quite well-behaved quantity, and we can say that this quantity is equal to the average number of Bell pairs, which we can extract from intermediate states for any choice of quantum state. Good thing, but this is highly complicated. It involves a square root. Like this is basically absolute value of tau log tau, but we take absolute value. So this guy is very difficult to calculate in many, especially in gravitational sense. So this is a good quantity, but it's like, I mean, I'm not going to talk about this. But okay, so actually, finally, I just mentioned some application of pseudo entropy. This first one is so we can, yes? Yeah, okay, thank you. So we have some initial state phi and initial state of psi and final state of psi. Final state of phi, and we have some intermediate here. So we decompose this intermediate state in terms of the number of EPR pairs and take average of this EPR state. So intermediate states just we insert between this inner product. And this is we take this ratio as a probability distribution, and that compute this. And yeah, so this pseudo entropy is generalization of entanglement entropy. It satisfies the area law, but also it satisfies area law. But maybe interesting thing is to take a difference between the pseudo entropy minus averaged entanglement entropy. How this quantity is different from entanglement entropy. And we find that this is always negative for if two guys are same quantum phase. If two guys are same quantum phase, this is always negative or zero. But what happens if they belongs to different quantum phases? So it's in an explicit calculation in this most typical model of quantum phase transition, quantumizing spin chain with transverse magnetic fields, we can confirm that if we calculate this pseudo entropy, when this one state, there are two states, first state or second state. First state is, for example, paramagnetic phase, and second state is other phase, ferromagnetic phase, then this quantity can be positive. But if both are all same, if both belongs to the same phase, it's always this negative. So that way, somehow this quantity plays a role of quantum order parameter, we expect. And there are heuristic interpretations. So you have one phase here, another phase here. And because there is a phase transition, there is some critical point here, and there's a gapless degree of freedom here. And so we measure entanglement along this subsystem. So it's nicely pick up this gapless degree of freedom. So if we compute this entropy here, so this is a complete gap, so nothing interesting. But only here it enhances. In gravity viewpoint, there is some ADS spacetime it opens up along this interface, right? And that's intuitively explain why this enhancement of pseudo entropy occurs. And we can also think of more topological phases and so on, but this technical I'm not going to talk about. And finally, I'd like to mention our latest work about realization of this phase transition, entanglement phase transition using pseudo entropy. So there is an interesting these days developments about so-called measurement-induced phase transition or entanglement phase transition. And that's related also quantum circuit. If we start with some less entangled, disentangled state and run by some random circuit or a very chaotic circuit, then entanglement grows. Okay, initially zero entanglement, but it's growing under linear T, like it's growing under so that it's proportional to time. But the new thing is we can put a lot of projection operation, projection measurement. Then, of course, projection measurement reduces entanglement. And if we have a lot of projection measurement, of course, it becomes trivial. So entropy becomes constant. Just don't grow. But there is a nice thing. If we control this amount of projection, there is a critical point. So we have some logarithmic time evolution of entanglement. So this is about 1D spin chain. And usually it's a linear T growth, but there is some interesting critical point. So our motivation to understand this thing from the viewpoint of gravity side, and we start with this completely disentangled state and act some quantum circuit. So the disentangled state is actually realized by so-called putting some brane in the space-time. It's called the end of the world brane. So we have a space-time, we just cut some region and forget about the other part. Then it's really disentangled everything. It becomes product state here. And then non-trivial thing is the dynamics of this brane. This is a Euclidean part, imaginary part, but it's called the Lorentzian part. And we introduce some new ingredient that it's a kind of non-unitary dynamics. Otherwise, always entropy is increasing by this kind of chaotic circuits it's running here. So once that is realized by putting some extra scalar field on this brane. So this is some brane which we project to state, and we put some scalar field, and then actually we can control entanglement. But more precisely, it's a pseudo entanglement because so we are looking at this kind of setup. So we have two boundaries here, another boundary, and we change this boundary condition between these two guys. If these two guys are same, this is a usual quantum state, and it always grows linearly, linear T. But we can change if we change this two boundary condition by putting some scalar field, some matter on brane, some deformed brane, then we can control entanglement so that we can realize also log T behavior and constant behavior. And this is simply so this part is linear T because it involves a black hole, and this part is involved some more ADS, but with a gap to ADS with some mass gap. And in the middle, this is a critical point. This is a real usual ADS. It's called Poincare ADS. It's like it opens up this infrared degree of freedom, and that gives a log T. And so that way, so the pseudo entropy also can capture these phase transitions.
I guess. How does delta P, like, I didn't understand what delta P.
So yeah, sorry.
How does that correspond to like some sort of like how often you're measuring?
Okay, yes. So delta phi is so we actually put some scalar fields on this plane, and we have some boundary condition. This phi equal, for example, 0 here, but this here phi equal delta phi. Maybe phi equal phi 0 here, and phi equal phi 0 plus delta phi. Then there is a non-trivial profile of this scalar field, and that actually gives this difference, and that actually here in terms of this brane language here, it becomes imaginary source, I phi-like behavior. It becomes non-unitary dynamics, we expect, and that we hopefully related to some kind of this kind of dynamics. Yeah. It's like this. So, but I just omitted this technique. Okay. Yeah. I think I'm done. So I just summarize conclusion. So the pseudo entropy, which I talked in the latter half of my talk, is a generalization of entanglement entropy, and this depends on both initial state and the final state. And this is in general complex valued. And for particular case, diagonalized case, we can interpret it as a amount of quantum entanglement in intermediate states. And the good thing is that in ADS-FT, we can calculate it as a minimal area surface, generalization of holographic entanglement. And also, it acts as some quantum order somehow. And yes, we can think of many interesting future directions. But this quantum information meaning of this complex value. So imaginary part is not so clear, so it's quite interesting. But in the light of these recent developments of this pseudo entanglement, so here what we had in the sort of maybe we can interesting to think pseudo entanglement. So this pseudo is our pseudo, and this pseudo is your pseudo, like that. And yeah, also physics, also this might be interesting to apply to this digital space and where we can understand pseudo entropy as an emergent time in holography. Do have some works in that direction. I think I'll stop here. Thank you very much.
Question.
Could you give an even higher level view of why did you define pseudo entropy? Just for
Okay. Yeah, I mean, so this is actually, I mean, to understand geometry in terms of some entropic quantity. And so far we covered the static, completely static anti-digital space, and also this Lorentzian time evolution. But actually there is at least theoretically very important another object. It's like Euclidean time dependent anti-digital space, which has many new solutions. And what this, minimal surface means in area, minimal surface area means in such a geometry. And that leads to this kind of code. Yes.
So with the measurement into space transitions, I mean, I imagine the original model is that you have a circuit which is completely unitary, and then you introduce measurements. Well, here the computation you had the Euclidean CFT to begin with, and then you also added some unitary dynamics, right? So why not consider the Lorentzian?
Yeah, but you can just cut out this part. This is just a way to prepare initial state. So we have a Lorentzian time equation here, and we are doing here as a Euclidean path integral. So yeah, so anyway, this Euclidean thing is quite useful to prepare all this quantum state. If everything is, Lorentzian, so anyway, we need always specify initial state. We can go down, but still, so it's kind of endless. So that's the reason we use this kind of trick.
But I thought that the embedding, just on the next slide, you seem to have done computation in the embedding space that is Lorentzian, right? So the boundary CFT was was Euclidean.
Yeah, this is the Euclidean setup.
Yes.
But here we cut here and we go to Lorentzian signature.
Okay.
Yeah. So we just only pick up this.
When you have the argument for why the pseudo entanglement can capture phase transitions, you have this picture in the next slide.
Yeah.
That what you said something like A captures the gapless point.
Yeah.
But so do you actually mean that you're somehow tuning the parameter of the Hamiltonian along that blue line there?
Sorry, this direction.
Yeah.
This direction is a translational invariant, we assume.
Right.
So we have Hamiltonian in this direction, and this Euclidean time evolution creates this state psi 2 here, and other evolution is created by psi 1.
Okay, so should I imagine something like if there is phase coexistence, then there should be that kind of region A where you have the gapless?
Yeah. So if we have some two different phases, there's a border, and you can choose A as any part of this border, and so you can pick up this gapless one. Yeah.
Is pseudo entropy related to the Aharonov's two-state vector formalism in some sense?
Okay,
is
so
that why it's related to weak values?
Okay, I see. Yeah, it should be related to some correlation, weak value correlation function. But I'm not so much familiar with what
I see.
Exactly the quantity you mentioned. Maybe you can tell me.
Yeah.
Do you run into trouble with the fact that the logarithm of, because you don't have like real matrices anymore, right? Or symmetric matrices.
Yeah.
The logarithm is not unique.
Yeah, you're right. So practically what we do is we can just case where this is well defined, like real value, and then there is some parameter, and we can change this parameter, and then analytical continue.
Oh, there's
Analytical.
some limited
But
process.
from the beginning, there's ambiguity of logarithm. But anyway, the meaning of imaginary, that is related to imaginary part. And so that's, I mean, I think involves that kind of ambiguity. Yeah, so we still don't know.
Okay, so there's
Well,
some actual issue.
Yeah, yeah. But in space-time picture, sometimes there is some kind of sphere appears. And this, you have a log, there are many branches, different imaginary parts. But that's corresponds to rotating around some cycle. There is such a also geometrical interpretation. Okay.
Any more questions? If not, let's thank Tadashi again.
Thank you.